Draw the shear and moment diagrams for each member of the frame. To begin, I'm going to convert my point load, distributor load into point load. In this case, our length of member CD is 5 meters because we have 3x4 triangle, so it's going to be 10 kilonewton. And then I'm going to convert my point load into horizontal and vertical components, which in this case is going to be the opposite. So we're going to have 4 divided by 5 times 10 kilonewton, going to give us 8 kilonewton, and then vertical is going to be 6 kilonewton. After that, we need to find our external action forces. There is a roller at A and a pin connection at D. As I'm in the forces and X direction, I have a solution for dx as negative 8 kilonewton. By taking moment about the point T, I found solution for AY as 12.5 kilonewton. As I'm in the forces in Y direction, I have solution for dy as 13.5 kilonewton. Now that I have all the external action forces, I can start solving for each beam or member. I'm going to start with member AB by drawing a free body diagram. For member AB, I'm going to have AY at A. At B, I'm going to have both a horizontal and vertical reaction plus a moment because it's a fixed connection at B. To solve for values of BY, sum the forces in Y direction, and solution for BY is simply 12.5 kilonewton, or BX in this case is going to be 0 kilonewton. By taking moment about the point B, I have solution for moment B as negative 37.5 kilonewton meter. I have all the required forces for member AB. I can proceed to member BC. But before I do that, I still have to find my forces perpendicular to the beam in order to draw our shear and moment diagram. So we're going to have a vector that is perpendicular to the beam, A prime and a B prime. By using trigonometry, I found the solution for A prime and B prime as negative and positive 77.5 kilonewton. Because joint B for member AB didn't have a horizontal force, member BC isn't going to have any force as well. And because point B doesn't have any horizontal force, C as well is not going to have any. Reason being, there is no other horizontal external force acting on this member. As I'm in the forces in Y direction, I found the solution for C at 7.5 kilonewton. Taking moment about the point C, I found a solution for moment C as 47.5 kilonewton meter. I have all the required forces for member BC. Now we can proceed to member CD. I have all the required forces for member CD. The only thing I need is vectors perpendicular to the beam in order to draw our shear moment diagrams. And I've named these as C prime and D prime. Converting our horizontal and vertical components to perpendicular to member CD, we have our solutions for C prime as negative 4.5 kilonewton and for D prime as 14.5 kilonewton. Now, using all these values, we can proceed to drawing our shear and moment diagrams. Beginning with shear, for member AB, we have A prime as 7.5, so we're going to begin at 7.5 kilonewton. Nothing's going to happen for the course of 5 meters. And then we have a positive 7.5 kilonewton, which brings us to 0. That means that this member is correct. After that, we have a positive B prime, by plus negative 5. So 5 take away 12.5 as 7.5. We're going to go up 7.5 points, and then nothing's going to happen for 2 meters. At that time, we're going to get pushed down by 10. So we're going to come down to negative 2.5 kilonewton, and then nothing's going to happen for the next 2 meters. And then we have downwards 5 kilonewton, and then upwards we have Cy, which is 7.5. 5 take away 7.5 is 2.5 positive, which is going to bring us upwards to 0 mark. I mean, this graph is correct. And then for our final number CD, we have C prime, which is negative 4.5. So we're going to go down 4.5, and from there nothing's going to happen again. Oh, pardon me, this is a uniform distributed load. So we have 4.5 down, and from there we're going to have go down 10 kilonewton, which is going to be negative 14.5. It's going to be first order curve over the distance of 5 meters, and from there we have our dy, which is positive, d prime, which is positive 14.5, and it'll bring us all the way up to 0. This means our calculations for this section were correct as well. Now we can draw our moment diagram. So for our moment diagram, we're going to begin at 0, and then we have moment B, but before we have moment B, we have this area 7.5 over the course of 5 meters. So 7.5 times 5 is 37.5. So we're going to go upwards 37.5, and from there we have moment B, which is counterclockwise, going to bring us down to 0 mark. That means this calculation is correct as well. And now for the next part, initially we have our moment B, which is going to take us upwards to positive 37.5. From there we have this positive area, which is 7.5 times 2, bringing us to 52.5. Then we have this negative area, which is 2.5 times 2, comes up to be 5. So over the course of 2 meters, it's going to bring us down by 5, which is 47.5. And from this point, 47.5, we have moment C. And moment C is counterclockwise, therefore we're going to go down by 47.5, bring us to 0. That means this calculation is correct as well. Now, next we have a trapezoidal area. So we're going to have two negative areas. So first one is negative 45, 4.5 times 5, and second one is half times 14.5 times 5. After that, we have a solution as 58.75. But before we do that, first we have our moment C at point C. In this case, we have clockwise. So we're going to go upward 47.5. And from 47.5, we're going to go downwards 58 point. Any mistake I made over here when I was letting you guys know what the area of a rectangular triangle is that I mistakenly added here 14.5. In fact, it should have been 10. So that has been corrected. And adding these areas together, we get a solution as 47.5. negative because our areas are negative. So that brings us all the way to our point 0, and in this case our curve is concaving downward and it's going to be second order curve, and that means our